Hello everyone. Welcome back to another journey into the world where numbers tell stories. Let me start with something fun. Have you ever wondered how your school calculates the average marks of your class? Or how cricket commentators instantly announce the average runs per player during a match? No one's actually counting all those runs in their head. That's statistics doing its magic. So, today we'll explore how to find the mean, also called the average, but for large data sets that are grouped. You already know the basic idea. The mean is the total of all observations divided by the number of observations. Mathematically, it's written as x bar equals summation of fi xi divided by summation of fi. Here, xi means the value of the data, fi means its frequency, and that Greek symbol sigma means add them all up. It's like taking everyone's scores, multiplying them by how often they occur, adding everything together, and dividing by the total number of people. Think about it. The mean helps us describe the center of any data, whether it's your test scores, daily temperatures, or even your screen time. The mean shows what's typical in the group. In short, the mean is the heartbeat of statistics. So, now that we've revisited what the mean really means, let's see how it works when our data isn't just small numbers, but large sets grouped into classes. Alright, imagine your teacher wants to find the average marks of 30 students, but instead of listing every single score, she groups them 10 to 25 marks, 25 to 40 marks, and so on. Each group is called a class interval. To represent the whole group, we take its class mark, which is simply the midpoint of that interval. The formula goes like this: xi equals upper class limit plus lower class limit divided by 2. Easy, right? Now, once we have all those class marks, we multiply each one with its frequency. That is, how many students fall in that class. Then we add them all and divide by total frequency. So our formula is the same. X bar equals summation of fi xi divided by summation of fi. For example, using data from our table, we got the total of fi xi as 1860 and total frequency as 30. So the mean equals 1860 divided by 30, that's 62. That's the direct method in action. It's like finding the class average by multiplying each group's representative mark by the number of students, adding them all, and dividing by the total students. Clean, simple, direct. But what if the numbers are huge and multiplication becomes messy? Don't worry, we've got a smarter shortcut coming up. Now, sometimes multiplying large numbers like 92.5 into 6 or 77.5 into 6 gets, well, exhausting, and your calculator battery might even give up on you. That's where the assumed mean method comes in to save the day. Here's the trick. Pick a value near the middle of your data. Call it the assumed mean, denoted by A. Then calculate the deviation of each class mark from this assumed mean. We write this as di equals xi minus A. Now multiply each deviation di by its frequency fi, add all of them up, and divide by total frequency. Finally, add the result back to the assumed mean. So the formula becomes x bar equals a plus summation of fi di divided by summation of fi. For instance, if we take assumed mean as 47.5, total fi di as 435, and total frequency as 30, then x bar equals 47.5 plus 435 divided by 30, which gives us 62 again. Perfect. Think of it as adjusting everything relative to an easy reference point, like saying, let's measure everyone's height compared to the average height in class. It saves time without changing the result. But hey, can we make this even faster? What if I told you we could do it all with smaller numbers? Let's meet the step-deviation method. Okay, mathematicians, ready for the turbo mode? In the step-deviation method, we scale down our deviations to smaller, easier numbers. If all deviations share a common factor, say, the class width h, we divide each deviation by h. That gives us a new column, ui equals xi minus a divided by h. Now our mean formula becomes super compact. X bar equals a plus h into bracket summation of fi ui divided by summation of fi bracket close. Let's plug in our example. I equals 47.5, h equals 15, summation of fi ui equals 29, and summation of fi equals 30. Then x bar equals 47.5 plus 15 times 29 divided by 30 equals 47.5 plus 14.5 equals 62. Yes, the same answer again, only faster and simpler. This method is like turning your maths homework into a shortcut recipe. Same flavor, less effort. The key ingredient? Equal class widths. So we've learned three methods: direct, assumed mean, and step deviation, all giving the same delicious result. Let's see how they compare side by side. Here's the golden rule. Whichever method you choose, if done correctly, the mean will always be the same. The direct method is like manual driving, full control but needs more work. The assumed mean method is semi-automatic, easier when data is large. And the step deviation method? That's your full auto car, smooth, effortless, and quick. Mathematically, all three use the same logic but in different forms. Direct. X bar equals summation of fi xi divided by summation of fi assumed mean. X bar equals a plus summation of fi di divided by summation of fi step deviation. X bar equals a plus h into bracket summation of fi ui divided by summation of fi bracket close. Choose the one that fits your data scale and interval pattern. Efficiency is key. Now, let's bring this to life with a real-world example. Data on female teachers in India's rural schools. Let's put our learning into practice. Here's some real data. The percentage of female teachers across rural areas in India. We'll calculate the mean using all three methods. Given A equals 50, H equals 10, summation of Fi equals 35, summation of Fi xi equals 1390, summation of Fi di equals negative 360, and summation of Fi ui equals negative 36. Now, direct method. X bar equals 1390 divided by 35 equals 39.71. Assumed mean method. X bar equals 50 plus. Negative 360 divided by 35 equals 39.71. Step deviation method. X bar equals 50 plus 10 into bracket negative 36 divided by 35 bracket close equals 39.71 again. All three roads lead to the same mean, 39.71%. So, what does this mean? It tells us that, on average, nearly 40% of teachers in rural primary schools are women. A powerful insight into gender representation through statistics. Now, let's see one more practical situation. Something close to every cricket fan's heart. Alright, math champs, here's the grand takeaway. We've learned how to find the mean of group data using three powerful methods: direct, assumed mean, and step deviation. All of them lead to the same result. The only difference lies in how you choose to simplify your calculations. The direct method is your base, the assumed mean method saves effort, and the step deviation method is your ultimate shortcut. Each one is equally correct. Just pick the right tool for the job. And remember, the mean isn't just a number. It's the story of your data told in one simple value. Whether it's exam scores, weather temperatures, or cricket statistics, mean gives you the heartbeat of the dataset. And that's how we calculate the mean of group data. Three methods, one answer, infinite applications. In the next video, we'll move ahead to the median of group data, where the middle value takes the spotlight. Until then, keep counting smart, not hard.